All right, so for the last topic of today, Gauss quadrature, so basically numerical integration. So what if we want to do the integral from a to b of some function, and we cannot really, I mean, in 1D, you can always do the approximately a sum of, you've probably done this type of approximation before. For example, when you evaluate the value of f at some points times h. So if you divide this on into different bins, right? And you can always approximate the integral by, this is like the opposite of the way you get to the definition of the integral, right? So you can get the height of each of these little bins and then sum, let's say that h is the width of this, then you can sum all of those little rectangles and then you'll get an approximation of the integral. It gets a little bit more difficult when you are in 2D. So in 1D, this could be really easy to do. And then it's convenient to map this this function to a given domain. So Gaussian quadrature are rules that allow you to integrate functions very accurately with very few points, but it only works on the -1 to 1 interval. And then there's tables that tell you, for depending how many function evaluations you want to do. So obviously this way of splitting the domain into a certain number of bins, it will work, but it's not the most efficient one. And then you would have to actually calculate what are the different xi values that you need in order to evaluate the function. So that's not very convenient. And these rules basically give you specific points that, depending on the amount of points that you want to evaluate, they will give you the best possible integration if it's a polynomial, at least. But it's used basically for anything, even though they were designed to integrate polynomials. And so you have the integral from -1 to 1 is the sum of some weights times the function evaluated at those specific points in the -1 to 1 interval. And you can look this up in Wikipedia. So for example, if you can only evaluate the function at one point, so if you only have one point to evaluate, then let's just do this. So if you only have 1 point, your best point is at x equals 0, or well, I'm using x here, this will become xi, but basically at 0 you evaluate your function, so this is f of at 0, right? And so for the 1 point, your best approximation is the weight, which is 2 times f of 0, that, right? If you have only one function evaluation. If you have two function evaluations, if you want to evaluate the function at 2 points, your best points are plus or minus 1 over square root of 3, which might be somewhere over here. So minus 1 over square root of 3 plus 1 over square root of 3, and this is the corresponding value, f at 1 over square root of 3, f at, well, minus, and then 1 over square root of 3. So if you have 2 points, then your best approximation is, and the weights are 1. So 1 times the function at minus 1 over the square root of 3 plus 1 times the function at 1 over the square root of 3. And let's just do one more. So what if we have 3 points to evaluate? So then your best points are 0 and plus minus square root of 3 over 5. So 0, which we already had there, and plus minus square root of, so this is minus square root of 3 over 5 and plus square root of 3 over 5. So for 3 points, your best approximation is, and this point has weight 5/9, so 5/9 f at minus square root of 3 over 5 plus, 8/9 of weight for the point at 0, so 8/9 f at 0, plus 5/9 f at plus square root of 3 over 5. And so on, depending on how many points you have, these are your best points. So that's basically it. And now we just need one thing. So what I said is, if you want to integrate something as a function of x between two arbitrary points, a and b, you would chop it in some way and then add the function value times the these bins. That would be one way of doing it. I said this is not very efficient. It's more efficient to have this type of selected points and selected weights to do the integration, but this only works in the -1 to 1 range where you have these Gauss quadrature points. So obviously what is next? Well, you need the isoparametric map, right? Because you have, if you consider 1D, then you have, in 1D you have your element that is in the x space, and then you have your corresponding element in the xi space, where the xi is actually from -1 to 1, right? And this one is from x1e to x2e. In this case, these are scalar, right? And so we want to do integrals in the -1 to 1 range, and we have this map, right? So we have the map between x and the xi, isoparametric map. And Jacobian, right? So we have the Jacobian of the isoparametric map, which is, in this case, because it's one dimension, just total derivatives of x with respect to xi, right? Which is just the sum of the derivatives with respect to xi times xif. So we have the map and the Jacobian of the map. So let's say we have some function, and we can have that function instead of x. So notice that here we want to do an integral over the domain omega e, which would be from x1e. So this is omega e, and this, let's call this omega parent. So of some function of x, d of x, right? And then what we would need to do is we would need to do an integral from -1 to 1 of the function, but in terms of xi, times the Jacobian, well, the inverse of the Jacobian, right? Because the Jacobian, actually not the Jacobian, times the, well, integrated over the xi. So that would be an integral from -1 to 1 of the function, but I just did a change of coordinates. So it's the same function, but change of coordinates. Right, times the Jacobian, and then integrate that over xi. And you can use then Gauss quadrature to do that, right? So that integral is just a sum of the function evaluated at particular points times the Jacobian at those points times the weights that I was talking about in the last one. This is actually in the Rieger's book in chapter 4. So that's how you can do it. Let me just do one clarification here, because there's two ways. How do you do this change of coordinates between g of x and g of xi? Well, let me just do an example. So let's say, well, let's do two examples. So example 1, let's assume that I have in this space x for my element. I have x1e and x2e, right? And I have also some value, let me use red, theta 1e and theta 2e, where theta represents a function, right? So because, actually, let's make it actually a function. Oh no. So that will be example one. Let's say we have something like this. And then we have our parent domain, right? So we have our parent domain that goes from -1 to 1. And then we can always just copy paste these values, right? Well, they don't look exactly the same, but maybe I need to something like that, right? And then obviously here let's say that we are interpolating with linear shape functions. So theta h is going to be directly, actually in this case theta h is already in terms of psi explicitly, right? Is sum of the shape functions in terms of psi times theta IE. So that's one example where you have a function also interpolated with the basis functions. So in this case, actually we don't even have the theta h as a function of x, right? We don't even have explicit expression for theta h as a function of x. So if I ask you to compute the integral of theta h as a function of x dx from x1e to x2e, I mean, that one you cannot even do directly because you don't even have this theta as a function of x. You only have the interpolation in terms of psi explicitly. In order to get it in terms of x, you would have to somehow find the inverse map, right? Because you have this map. You have the map that goes from psi to x, but you don't have the inverse map. So actually, in this case, it makes even more sense to do the integral from -1 to 1 of theta h of psi, because in this case we have the theta directly in terms of psi, right, times the Jacobian d psi. And the Jacobian is just from the definition of the isoparametric map, right? So we have x equals sum of ni psi xie, Jacobian equals sum of dni d psi xie. And in this case, the Jacobian is a constant, but in some cases, this will depend on psi. And then just use your favorite number of Gauss points and do that. Now, what if, so this is the least interest example. So what if I actually have a function that is very well defined in, let's say we have x1e and x2e, and I don't have an approximate theta, but I actually have the true theta. Let's say that I have this. This is theta, not h. This is not an approximated function. This is actual theta of x. Let's say I have that, right? And in that case, what I don't have, I still have my map here, right? But I don't have theta. I could always copy paste this theta and put it down here, but I won't have it explicitly, right? So in this case, I have theta of x explicitly, some function. Imagine that I tell you, theta is whatever, x squared plus 2x, something. And so I want to do the integral from x1e to x2e of theta of x dx. And I said, oh, this is the same as the integral from -1 to 1 of theta of psi Jacobian d psi. Well, I don't have theta of psi, so how do I do this? Well, you have the map. So what you can say is, think instead of integral from -1 to 1 of theta of x of xi, j d xi. And so this one will be, or approximately equal to the sum from the number of Gauss points. So let's just use a different one. Let's use g equals 1 to number of Gauss points of theta of x of xi Gauss point, right, times the Jacobian evaluated at that Gauss point, times the weight corresponding to that Gauss point. And so what you can do is, basically for a given Gauss point, so given a Gauss point, which is xi equals 0 or xi equals plus 1 over square root of 3 or whatever, you can evaluate then the x, the corresponding x. So get corresponding x corresponding to that Gauss point with the isoparametric map. So basically evaluate the isoparametric map, then you can go and evaluate theta of x for that value of x that you just calculated with the isoparametric map. So you don't have an explicit definition of theta in terms of xi, but again, given some value of xi, you can evaluate the corresponding x and then use that x to evaluate the theta. So it's not explicit, but you do have the theta as a function of xi. You just need to use the isoparametric map in between. And that's about it. So that's how you would compute integrals in 1D. And this is not just true for linear elements. This will be true for... So the Gauss integration is independent of the degree of the shape functions, right? So the Gauss point just gives you a recipe for integrating between -1 and 1, depending however many points you want to use. And then the isoparametric map and the Jacobian, they work equally well for linear or quadratic shape functions. In 2D, same as before, right? So we have some domain and we have the parent domain. And then we want to do integrals here. So we want integrals over the element here, but we are going to do integrals over the parent domain. In this case, we need the determinant of the Jacobian. So you have some function defined here, whatever that function is, g of x, then you can integrate that over the parent domain by just doing the change of coordinates. So you just need g of xi times the determinant of the Jacobian times the, this is basically just xi eta, right? So if you just write the double integral, this will be integrals from -1 to 1 of g of xi eta times the determinant, which is a function of xi times d xi d eta. And here you can also use Gauss quadrature because you have these two different integrations from -1 to 1, this little square. So you just need evaluate, like this integral is sum of g at a particular Gauss point times the determinant of the Jacobian at that particular Gauss point times the weight at that of that Gauss point. And in the Rigger's book, table 4.2, you'll find if you can only spend one integration point, then your best choice is to evaluate at 0, 0. If you have 4 integration points, then this is your best choice. If you have 9 integration points, these are your best locations and the corresponding weights. So it's just a matter of following the recipe. Now, what is the decision? How many points should you use? That one depends on the degree of the polynomial that you want to integrate. So these points integrate some polynomials exactly. So 1 point will integrate a degree 1 polynomial exactly, 4 points degree 3, 9 points degree 5, and that's it. So it's usually, so if you have linear quadrilaterals, then you need 4 points. Degree 1, I think it's, so that is, so a linear will have m equals 2, because it will be like to the 0 power and to the first power. So m equals 1 is just a constant. Does that make sense?